Hello everyone, good morning and hope you're having a nice time out there. Well, welcome again to the concluding part of our IUPAC nomenclature. For previous classes, we have seen nomenclature of binary compounds and tertiary and quaternary compounds. When we said binary compounds contain just two elements, while the tertiary contain three and the quaternary contain four. Now this time around, we'll be looking at the naming of complex ions and complex salts. In a general term, we call them complexes. So we differentiate them into complex ions and complex salts. And that's what we are going to be looking into for this particular. Now, I would not want you to be bothered by the terms, but as you go on in your study, you should try to understand what we mean by each of these. They might be coming new to you, but please take good note of them because you are going to need a bulk of them later in the course of the study. Now, when we say complex salts, a complex salt is an ionic compound with a complex ion. Then, what is a complex ion? A complex ion contains a metal ion surrounded by ligands. Then the next question we ask is, what are ligands? Now, ligands are electron-rich species or a species which with lone pair of electrons which can be neutral molecule, like you have ammonia without charge, water, carbon 2 oxide, nitrogen 2 oxide, or anions such as chloride, bromide, iodide, hydroxide, cyanide, or and hydride ion. Now, to put the definition in a simple term, we can say ligands are electron-rich species or species with lone pair of electrons, which can be neutral molecules or anions. Just to put it simple, you can get rid of the examples there, but I want to believe that the understanding of what ligands are takes us back to our understanding of coordinate covalent compounds. Now, any compound that is an electron donor and can participate in coordinate covalent bonding is a ligand, because what makes them ligand is the presence of lone pair of electrons which they can bond, and that is what also helps them to participate in coordinate covalent bonding. Now, what are the rules? We have a number of rules here when we come to naming of complexes. And I don't want you to bother yourself with these rules that I'll be reading. But by the time we get to the naming proper, the naming of the different classes, the complex cations, complex anions, the complex salts themselves, then I believe you understand each of these rules better. Now, when you want to name, the first rule says, there's a rule for naming complexes now. The first one says, in a complex salt, the cation is named first, then the anion. The cation first, then the anion. We're going to see that in our examples. Now, in a complex ion, whether cationic or anionic, the ligands are named first before the central metal ion, meaning you name the ligand before you name the central metal ion. Now, when you want to name a complex ion, each of the ligands is attached to the Greek prefixes of the number that is present. Meaning, if you are having one ligand, that tells you that it has to be mono, the name of that ligand. You are having two ligands, it should be di, whatever the ligand is. 3 tri, 4 tetra, 5 penta, and so on. Now, when anionic ligands are named, they are named such that their names end with O. You know your Br to be bromine, but when you want to name bromine as a ligand, it is named bromo. If it is F, you name it fluoro. Cl, you name it chloro. I, you name it iodo. Cn is named cyano. OH is hydroxo instead of the normal hydroxide you used to know. H minus is hydrido. N minus is nitro, or NO2 minus is nitro or nitrito, as the case may be. Then you have other ones like C2O4 minus oxalato, FCN minus thiocyanato, H2O alcohol, NH3 amine, then you have CO carbonyl. So also you have NO as nitrocell, as it is here. Now those are the few anionic ligands that we are going to be dealing with for now. And whenever you are to include them in the naming of compounds, always bear in mind that their names must end with O, with the exception of the neutral ones. All anionic ligands end with O, but the neutral do not. Please take note of that. Now, in naming anionic complexes, the name of the central metal is modified to end with the suffix ATE, 8. Now, but when you are naming a neutral or a cationic complex, the name of the metal is unchanged. It remains the way it is. We'll be seeing that in the few examples we'll be looking at now. Now, when two or more different ligands are present, the anionic ligands are named alphabetically. First, anionic first, the neutral ligands are also named alphabetically. That is in the order of the preference. Now, let us look at the various examples we have. Now, remember we said in neutral or cationic complex, like this one, the name of the metal is unchanged. Now, these ones that are carrying positive charges on them are cationic complexes. So with 2 plus they are complex. So when you name the metal there, this copper here, it remains copper. Fe here remains iron. Then Pt here remains what? Platinum. Now let's see how we name them. The rule is for anything, be it an ionic, cationic ligand, or complex rather, you name the ligand first before the metal. Now, in the case of NH3, normally you would know NH3 to be ammonia. But from our table here, NH3 is amine. And here you're having 4 NH3. That tells you that that should be tetraamine. Now the next thing you now do is that you have named the ligand. Now name the central metal there, which should be a transition metal, and that is copper. Now the copper is followed by the oxidation state of copper itself. And how do we determine that? Let's try seeing how we can go about determining the oxidation state here. Now, your copper is to be determined plus 4 into 0. Now, why 0? It is 0 because amine or ammonia is a neutral ligand. So the charge there is 0. So everything here has to be equal to plus 2 because the charge you have on the complex is plus 2, just as you have it here, plus 2. So that's why we have to equate this to plus 2. So in this sense, we see this would give us Cu plus 0 would be equal to plus 2. Hence, Cu equals plus 2. Hence the reason for the 2 you have in bracket here. Now, when we come to iron, as we have here, you are having 6 water molecules there. And remember, whenever you're naming water, water is named Haku. Water is named Aku. So, in naming water here now, we call it Hexa-Haku because 6 in Greek as is named the prefix Hexa. Now, Hexa-Aku, remember this is cationic, and this one remains ion. So the next thing we look out for is what will be the oxidation state of iron. That would be Fe plus 6 into 0 will be equal to plus 2. Now this would give us Fe plus 0 equals plus 2. Hence, our Fe would be equal to plus 2. Hence, the plus 2 oxidation state of iron in brackets as we have it here. Now, the last example on cationic complexes is what we want to look into. So, remember, from our table, we have amine, we have nitro, and we have chloro. Now, let's try to see which one of them is neutral and which is anionic. Now, this is our amine. It is neutral. This is our nitro. It is anionic. And we also have chloro, which is also anionic. So in naming, we have to name the anionic complex, anionic ligands first before we name the neutral ligands. So in order to name down, chlorine has to come before the nitro, then we deal with the amine lastly. So let's see what that will look like. Now, here you are having dichloro. Chlorine comes first, it is anionic. Nitro, because you're having just one NO2. Then amine, you have two of them, we'll call that diamine. Now, the next thing we will do is determine the oxidation state of platinum. From here, we have Pt plus 2 into 0 plus minus 1, which is the charge on your NO2. That's as written up there as a NO2 minus, like we have it here as NO2 minus this. So the charge is minus 1. Now, when we come back to this, then we have our chloro 2 plus, open bracket, minus 1, because chloride is also minus 1 charge. So in that sense, our chloride takes 2 because you're having 2 chloride ions there. So everything here should be equal to plus 1. Now that gives us Pt plus 0 minus 1 minus 2 equals plus 1. Then you have Pt minus 3 equals plus 1. Then your Pt would be equal to plus 1 plus 3, such that the oxidation state of your platinum would be equal to plus 4, hence platinum 4. Now, those are complex cations. Now, let's look into the case of our complex anions. Complex anions. Now, we say that whenever we are naming complex anions, let's review the rule again. In an anionic complex, the name of the central metal is modified to end with 8, with the suffix 8. Any metal that is present in a complex anion must end with ATE. That's just what we are trying to pull here. It must end with ATE. Now let's look at the examples. Here we are having FeCN6. Cn is an anionic ligand with charge of minus 1. You can review back to the table. Charge of minus 1. Now, that should be hexacyano. Hexacyano. 6 is the hexa. The Cn is cyano. Now, the Fe now is ion normally, but being a complex anion, it must end with ATE. No, now, we cannot change ion to ionate, so we refer back to the Latin name, which is ferrite. So normally iron is called ferrous. So because the name has to end with ATE now, we call it ferrite. Then the next thing we do is, what will be the oxidation state of iron in FeCN6? So let's try to decide that. Fe plus 6 into minus 1 for the Cn minus, everything will be equal to minus 3. So this would give us Fe minus 6 equals minus 3. So we have Fe equals minus 3 plus 6, such that Fe equals plus 3. Hence, oxidation state of plus 3 in brackets. Now, for the next one, it's still hexacyano. If you determine the oxidation state of iron, then that will be 2. So you have hexacyanoferrite. The next one, oxidation state of zinc there is also 2 because OH is minus. So we have Zn minus 4 equals minus 2. So calculating Zn there will give you plus 2. Now we have zincate 2 because the name of the metal must end with ate. Now let's look at this example here. You have H2O, water, which is alcohol, as your neutral ligand, and you have OH as your anionic ligand. Remember, anionic ligand must come before the cationic, before the neutral ligand. So in naming this one now, we call it tetra because of the 4 you have in here. Tetrahydroxo. Tetrahydroxo. Then your 2 here gives us diaco for H2O. Then this being aluminium must end with ATE. Aluminium must end with ATE. So in order to modify that, we call it aluminate. So we call this tetrahydroxo diacoaluminate 3 ion, as you have here. If you calculate the oxidation state of aluminium from here, it should give you Al plus 2 into 0. That's the oxidation state of the water is 0 because it's neutral. Plus 4 into minus 1. Everything equals minus 1. That's the charge on the compound there. So you have Al plus 0 minus 4 equals minus 1 to give us Al minus 4 equals minus 1, such that your Al would be equal to minus 1 plus 4. So Al equals plus 3. So oxidation state of aluminium there is 3. Now the next example here is also a complex. So you have BH4 minus. Hydrogen there is going to be named hydrido. You can review back on the table. So you have 4 there, that will be tetrahydrido. Because it's carrying a negative charge, you call that, this is boron in the normal element name. But because of the negative charge on the complex here, you call that borate, as the case may be. So we call that tetrahydridoborate 3. Tetrahydridoborate 3. Now, the few other examples we have, naming, you have amine, you have chloro, you have bromo. Chloro and bromo are anionic. They come before the amine. So this is tribromo because B comes before C. So we name alphabetically by giving preference to the anionic before the cationic. So tribromo dichloroamine. The amine here is not having any other thing outside, so it's just one of it. So we call it amine. Chromate 3. If we calculate the oxidation number of chromium here, amine here is 0, chloride is minus 1, you have 2 of it. Bromide is -1, you have 3 of it. That's giving us chromate 3 ion. Those are the anionic complexes. Now let's look at the neutral complexes we have. They are complexes. They are neutral because they do not carry any charge. The rules still follow, but we revert back to the fact that being neutral, the name of the element is just mentioned as it is. You do not change the name of the element to end with 8. So we have chloro coming before amine here. So this is tetrachlorodiamine platinum. So calculating the oxidation state of platinum here is 4. So we have platinum 4. This is tetracarbonyl nickel 4. Then you have trichlorodiamine. It should be diamine because you're having 2 ammonia here. So trichlorodiamine cobalt 3. Trichlorodiamine cobalt 3. Now the last category is the complex salts. Now this is what we refer to as cation. Because it precedes the complex, it has to be named first. And when you are having this one, it's named last. So also as you have here, this is just named chloride. Let's go of the name. But how do you know now if this is if the complex here is going to be cationic or anionic? Let's try to split the compound into the ions present. Now this one should give you 4, should give us 4K plus. Then plus the whole of this ligand here, of this complex here rather, you want to check what the charge on it is going to be. Now, this one now should take a charge of 4 minus. So that it balances up with the charge of the potassium ion that you are having here. Now, in order to do such now, because this one is taking a charge of 4 minus here, your Fe is not going to be named ion, but ferrite. Please, let's get it clear. This one is going to be named ferrite because when you split it, it's going to be negative here. Now, when we come to this particular example, if we split that, it should give us this having a charge of 4 plus 4 Cl minus. So because this one now is a cationic complex, this one, so the name will not change from platinum. It will remain what? Platinum. So these 4 will not reflect in the naming of this here. Just call it chloride. So also the 4 here will not remain. It's just called what? Potassium. So the same thing applies to the last example here. SO4 is always SO4 2 minus in its the normal what's it called, anionic radicalities, meaning that this one here is going to take 2 plus charge on it. So being 2 plus charge, you call this one just copper. You call it copper and nothing more. Copper 2. If you calculate the oxidation state there, it's going to give you plus 2. So you call it copper 2 tetraoxosulfate 6. So this is naming of complexes, and I was expecting this to be the concluding video, but it would not be the concluding video because we still need to look at various examples, how we can use the name to generate the formula of the compound. I'm going to do that just immediately now, and you'll see it alongside the naming of complexes as in this one that you are viewing presently. Thank you.